Now I shall classify the fluids based on the Newton's law of viscosity with the help of a graph shown in figure. Y-axis is chosen as shear stress and x-axis is chosen as velocity gradient, that is du by dy. Obviously the straight line linear relationship line fluid is nothing but Newtonian fluid, already given the examples as air, water, mercury, etc. This is non-Newtonian fluid. Not having a linear relationship between shear stress tau and velocity gradient. This is also known as a dilatant fluid. This is also non-Newtonian fluid. Also known as pseudoplastic. This is ideal Bingham plastic. Obviously x-axis correspond to the ideal fluid. X-axis correspond to the ideal fluid. Remember, that is mu is 0, shear stress will be 0. And y-axis will correspond to the ideal solid. Ideal solid where there is no velocity gradient at all, even under the application of very high shear stress. So that is how we can distinguish between solids and fluids. Fluids deform continuously under the action of the slightest shear stress or tangential stress or viscous stress. So this is how we can classify the fluids based on Newton's law of viscosity. Air and water are example for the Newtonian fluids where mu is a constant. In fact, the subject that deals with such classification of fluids is known as rheology. Now I shall define another property called as kinematic viscosity. Denoted as nu. It is defined as the ratio between dynamic viscosity mu and density. That is, kinematic viscosity is mu by rho. Its units will be Newton second per meter square divided by kg per meter cube. Resulting unit will be meter square per second. Dimensional formula is L square T power minus 1. This is the dimensional formula. In fact, there are some other subsidiary units meant for dynamic viscosity and kinematic viscosity. For mu or dynamic viscosity, poise is used. 1 poise is equal to 1/10 of Pascal second. Similarly, for nu kinematic viscosity, it is Stoke, that is 1 centimeter square per second or 10 power minus 4 meter square per second. Stoke is meant for kinematic viscosity, poise is meant for dynamic viscosity. Earlier already defined Prandtl number, very important number in heat transfer, is kinematic viscosity divided by thermal diffusivity. Alpha is thermal diffusivity. Prandtl number is a dimensionless number. used in both free convection and forced convection. Both nu and alpha have got the same units of meter square per second. No slip condition of viscous fluids. This concept is very important while dealing with the drag force exerted by a flowing fluid over a stationary solid surface. Suppose that a stationary plate is there. A fluid is moving with certain velocity v infinity. There is a boundary layer development, hydrodynamic boundary layer, where we find velocity gradients in the normal direction to the plate. There is one particular layer of the fluid which gets attached to the solid surface, stationary plate, and this plate has got zero velocity. That is, when a viscous fluid flows over a solid surface, the fluid elements adjacent to the surface attain the velocity of surface. In other words, the relative velocity between the solid surface and the adjacent fluid particles is zero. That means the fluid layers are not slipping. This phenomenon is called no slip condition. So, as the fluid is flowing past a solid stationary surface, there is one layer of the fluid that has zero velocity because it gets attached to the plate and hence cannot slip over it. This is called no slip condition. Now I shall define another important property called as surface tension, sigma. In fact, there are two different kinds of intermolecular forces in fluids. Number one, cohesive forces, and number two, adhesive forces. The force of attraction between the molecules of a liquid, by virtue of which they are bound together to remain as one assemblage of particles, is known as force of cohesion. So the intermolecular attractive forces between the same liquid molecules is known as cohesive forces. This property enables the liquid to resist tensile stress. On the other hand, the force of attraction between unlike molecules, like between the molecules of a different liquids or between the molecules of a liquid and those of a solid body or container, when they are in contact with each other, they are known as force of adhesion. This force, adhesive force, enables a fluid or a liquid to adhere to a solid body or a surface. In fact, surface tension is due to the intermolecular cohesive force. I consider a liquid having contact with the air. This is a free surface of the liquid. If we consider interior molecule, it is being pulled from all the directions with the same magnitude of the force, and hence net force on this interior molecule is 0, because it is equally pulled from all sides by the adjacent molecules due to the cohesive nature of the forces. Net force is 0. But whereas if you consider a surface molecule, this force is balanced by this one, but whereas the downward pull is unbalanced. The downward pull of the interior molecules over the surface molecules is unbalanced. So there is a net unbalanced downward pull exerted by the interior molecules over the surface molecules. So the top layer of the liquid is like a stretched rubber membrane under tension. This tension is called as surface tension. So surface tension is due to intermolecular cohesive forces. The surface layer of liquid is like a stretched rubber membrane under tension, and this tension is known as surface tension. Sigma. Units are Newton per meter. And when a small loads are gently placed over the surface of the liquid, they can be balanced. For example, this is the surface of the liquid, surface layer, free surface layer. When a small pin is placed over the surface of the liquid, gently placed, this could be balanced. The weight of the pin could be balanced by the sigma, the tension in the surface. The weight, downward weight of the body, a small body. For example, a small insect could walk over the surface of the liquid because of the tension prevailing over the surface of the liquid. Or a droplet of water would assume spherical shape because sphere has got a minimum surface area for a given liquid due to the surface tension. So these are all the examples that could be given to the surface tension, like walking of a insects over the liquid layer, or a small pin gently placed over the liquid is balanced due to the surface tension, or spherical shape of the water droplet, or spherical shape of the soap bubble, or cylindrical shape of the jet of water. These are all the examples that could be given to the surface tension. The surface tension value of water in contact with air at 20 degrees centigrade is 0.073 Newton per meter. So this is an insect. I have shown there, insect walking over the surface of the liquid, free surface, because of the surface tension. Now examples of surface tension. I consider First one, to calculate gauge pressure inside a water droplet. I consider a water droplet of radius r. As I had mentioned earlier, the droplet assumes spherical shape because of the surface tension. Because for minimum potential energy, any system will assume stable equilibrium with the minimum potential energy. So, the shape of the droplet is spherical. Now, if you consider the equilibrium of this droplet, the braking force is P gauge into projected area. This is braking force which tries to break the sphere into two hemispheres. The balancing force is surface tension force proportional to length, which is equal to sigma into 2 pi r. For equilibrium, for static equilibrium of droplet, P gauge into pi r square should be equal to the sigma into 2 pi r. Therefore, P gauge is equal to 2 sigma by r, Newton per meter square. Please note that this P gauge is a pressure inside the droplet in excess of the outside atmospheric pressure. Similarly, second case, for soap bubble, if you take under static equilibrium, the bubble has two layers of soap, inside air, outside air. This is P gauge. So surface tension is acting over the two lengths. That is, braking force is P gauge into projected area, that is pi r square, where r is the radius of the droplet. The balancing force for equilibrium is sigma into 2 pi r plus 2 pi r, it is 4 pi r. Please note that here sigma is acting at the inner layer and as well as the outer layer. This is the soap liquid. So sigma is acting at the outer layer of soap and the inner layer of the soap. Therefore, P gauge is equal to 4 sigma by r, Newton per meter square. Please note that this is a P gauge is a pressure inside the soap bubble in excess of the outside atmospheric pressure. Now I shall consider case 3, gauge pressure inside a cylindrical jet of water. If you take a jet of water which assumes cylindrical shape, consider L meter length of the jet. For equilibrium, I draw the figure. If this is L is the length of the water jet, inside pressure is P gauge inside the jet of water. So the braking force breaking the jet into two halves is P gauge into the projected area, that is 2R into L. The balancing force is sigma into 2L newtons. So please note that there is one stitch here, there is one stitch there. You can imagine that the surface tension force is like a stitch which is trying to prevent the breaking of the jet into two halves at the center. Therefore, equating the two forces for static equilibrium, P gauge should be sigma by R, Newton per meter square. So, the breaking of the jet of water is balanced by the surface tension force acting at top and bottom. Surface tension force is proportional to the length. So we had obtained three different cases. Inside the water droplet, the P gauge is 2 sigma by R. Inside the soap bubble, the gauge pressure is 4 sigma by R. Inside the cylindrical jet of water, the P gauge is sigma by R. Please note that this P gauge is the excess pressure inside the droplet or the bubble or the jet in excess of the outside atmospheric pressure for static equilibrium. Now I consider the another phenomena in fluid statics known as capillarity. If surface tension is due to the intermolecular forces of attraction called cohesion forces, the phenomenon of capillarity is due to the interplay of the forces of cohesion and adhesion. This phenomenon is due to interplay of forces of cohesion and adhesion. What is cohesion? Intermolecular force of attraction. What is adhesion? The extramolecular force of attraction between the liquid molecules and the molecules of the container, maybe glass or what, a solid surface. When a liquid is in contact with a solid, if the forces of adhesion between the molecules of the liquid and the solid, called as adhesive forces, are greater than the forces of cohesion among the liquid molecules themselves, the liquid molecules crowd or go towards the solid surface. So the area of contact between the liquid and the solid increases and the liquid is wetting the solid surface. Now I take this example. If this is water, this is air. If I dip a glass tube inside the water, this is a free surface, the water will rise in this fashion. This is called capillary rise. Now if the same glass tube is immersed in mercury, mercury would not wet the solid surface because here the adhesion is lesser than cohesion. So mercury will dip inside the glass tube. This is called capillary depression. In the water, it is rising. The water is rising inside the glass tube because here adhesion, that is extramolecular force of attraction, is greater than cohesion. Water is wetting the solid surface. Please note the difference. So, if the adhesive forces are greater than the cohesive forces, liquid will rise in the glass tube known as capillary rise. Now, I consider again the glass tube of diameter D. Water is rising inside the glass tube due to the capillarity property. What is balancing the weight of this liquid rising inside the glass tube? The surface tension property. If sigma is the surface tension, the weight of the liquid column rising inside the glass tube is balanced by the surface tension force at the top. So, for equilibrium of liquid column rising in glass tube, the equation is the weight of liquid column should be equal to the surface tension force. What is the weight of the liquid column? Pi r square h, the volume of the liquid, into specific weight should be equal to the 2 pi r sigma, that is into cos theta, where theta is the angle. Surface tension force is along this concave length. When it taken the component in the vertical direction, it becomes 2 pi r sigma cos theta. Therefore, h is equal to 2 sigma cos theta by Wr, where h is known as capillary rise. So many meters. We can note from the formula that h is inversely proportional to the r, that is implies smaller the diameter or radius of the tube, more the value of capillary rise. For water, theta is taken as 0 degrees, and for mercury, theta is 130 degrees. Cos 130 is negative. It means h will be negative. It means capillary depression. Mercury will get dipped inside the glass tube. Next phenomena what I consider is vapor pressure. All liquids have a tendency to evaporate when exposed to a gaseous atmosphere. The rate of evaporation depends upon the molecular energy of the liquid, which in turn depends on the type of the liquid and the temperature. The vapor molecules exert a partial pressure in the space above the liquid, known as vapor pressure. For example, if you consider a container, this is liquid. The molecules leave the surface of the liquid because of their molecular energy and accumulated in the space above the liquid. So these molecules will exert pressure over the surface of the liquid. This pressure is known as vapor pressure. So when the equilibrium condition is achieved, the rate at which the molecules are leaving the surface of the liquid will exactly be equal to the rate at which the molecules re-enter the liquid. The pressure exerted by the molecules of the vapor over the surface of the liquids is known as vapor pressure. The vapor molecules exert a partial pressure in the space above liquid known as vapor pressure. The vapor pressure of a liquid is a function of temperature only. And is equal to the saturation pressure for boiling corresponding to the temperature. So, as the temperature of the liquid increases, its vapor pressure also will increase. So, the phenomenon of boiling of a liquid is closely related to the vapor pressure. When the vapor pressure of a liquid becomes equal to the total pressure impressed on its surface, the liquid starts boiling. So it may be concluded that boiling can be achieved either by raising the temperature of the liquid so that its vapor pressure is elevated to the ambient pressure, or by lowering the pressure of the ambience to the liquid's vapor pressure corresponding to the existing temperature.